Slips.com, 100% listener-supported radio, and now we return you to your host.
You are back with David Mackey's Shiny Side Out on freedomslips.com. This is on the #1 listener-supported talk radio on the net. So push the donate button or subscribe to the archives for free. You can also just make a donation to that. It's easy. You can buy some merch. Buy some merch is really good.
Merch?
Yeah, there's t-shirts and mugs and things like that. You can do that, and that supports the station to a degree which is satisfactory. If you've liked anything at all that we've said or any other host has said, we do ask that you donate because it's not free to run the station. It's been going for more than 10 years. Mickey and I have been here since almost the beginning.
Damn you, Edison.
And it's really, really important that you donate to the station otherwise. And it has been receiving donations this whole time. But you know what? Like all those other people, there are groups that come and go. And we do ask that you, while you're with us, that you donate. Now, Mickey and I have our own donation capabilities. You can donate to us. Go to the website for details. Anyhow, we're going to ask you one thing and one thing only besides donating, and that is you listen to Revolution Radio. We're halfway through show number 536.
630 and 500.
Yes. And we're going to be talking about water. How?
Well, yeah, but why, Dave? I mean, that's just crazy stuff, right? I mean, why would you talk about water?
I mean, you think.
What? Well, like the moon. Okay, I want to draw. And
just because it's there in plain sight doesn't mean it's ordinary.
Exactly. So exactly. So I mean, we're born on this. Well, most of us are born on this planet.
Most.
And
speak for yourself, Mickey.
I know, right? And I bear my cross. And we take a lot of stuff for granted. I mean, you probably don't know why the sky is blue. Right? Now I can tell you, I won't. I want you to learn it for yourself.
Starts with a D.
Starts with a D. It's an atmospheric effect. There's actually a reason why the sky is blue, but
you don't explain it.
No, I'm not. But the moon. I mean, we look at the moon. Well, the moon is there. There it is. It's there, and we're here, and it's there. So
there it is.
That's a given, right? There it is. Water. Here it is. The atmosphere we breathe in. All these things we take for granted because they're there all the time. I mean, we don't really think about these things terribly much. I mean, some scientists...
You don't even think that the air is dense until you can wave your hand through it and feel the resistance.
Exactly. And I love, observing my children doing things like that, right?
Mm-hmm.
Where they ask a question, okay, well, this is what it is, and here, that makes sense, right?
That's right.
And then they're eager learners. They're really curious. They want to learn new things. They want to understand things, which is awesome. And in fact, their teachers tell me, which is very satisfying for me, that they are in fact very interested in learning and want to learn new things. But anyway, the point here is though.
That's because you never shut them down. That's why.
That's true.
That's right.
True. Always answer to the best of your ability.
Mm-hmm. Too many rabbits.
Just don't make it up. That's it. Get the rabbits out. But ultimately, though, you have to ask those questions. So you have to ask, okay, well, why though, and how? I mean, we've talked about the moon ad nauseum. I even wrote an article about it, which I've been trying to get published, but it'll form a chapter of my book when it comes out one day.
Oh, please.
There's so many mysterious things just about the moon, right? And then we don't even go into all the sightings and all the funny structures that have been found.
That's right.
We don't even touch on. I mean, we
don't ask questions, Mickey. What?
No, but why water? Well, water. Water as a chemical substance. Okay, especially within our atmospheric conditions, makes no sense.
Mm-hmm.
We'll go into some of the detail, but I just want to highlight a few things here, right? Water, it exists in all of its aggregate states. in 3 of its aggregate states on the surface of our planet in our atmospheric conditions. So
we have all
vapor,
3. That's right.
Yeah, we got the vapor, we got the liquid, and we got the solid.
Woo-hoo.
Right? That's a very narrow temperature range and a very narrow pressure range as well, right?
That's right.
Pressure, and temperature is very narrow in all 3 states these are the only states we ever knew about, right? But it is also interesting because water is at its most densest at 4 degrees Celsius. That's when it's most dense. Now that makes no sense at all, because normally any other substance, and I mean any other substance, is at its most dense when it is solid. Right? If something is a solid, then it's usually more dense than its liquid or its gaseous form, which means a solid will sink in its own gas, and it will also sink in its own liquid. That's right. Because its relative density is exactly higher, right? Water, not at all. Water is at its densest at 4 degrees, which is liquid. Yeah. 4 degrees Celsius, water is still liquid. It becomes less dense because it expands when it's solidly frozen, but it also expands when it's heated and vaporized, as it were. That's right. So again, let me say this again. It expands both on freezing or cooling, right? Yeah. And on heating. That's no other substance does this. There's no other substance that does this. It just doesn't do it. No. So you've all discovered that anyway. If you were to put water in a glass jar with a lid on, it'll crack the jar when it freezes because it'll exceed the space in the jar. Recently, a water bottle, a glass water bottle, a small one, only 200 ml, right? Sparkling water that I had put on the top shelf in my fridge, not freezer, fridge. Yeah. It must have been cold enough to freeze, God knows why, but it froze and exploded. Well, it'll do that. Which occasioned in the cleaning of the fridge. In occasion cleaning, yes. Which was good. That's your fridge trolls doing that, just to trick you, by the way. Clearly, that's what happened. No, but look, let's look at this though for a second here. Now, water is a strange substance and grows stranger still as we investigate it, and we will within the confines of this paper we're going to present to you. It is also the fundamental stuff of life. Fundamental stuff of life. Without water, well, we wouldn't exist in the way we exist today. It covers about 70% of our planet, and it's easy to think that it'll always be plentiful. However, and this is a big however, right? And this is part of the theme that we're talking about here as well. Fresh water, it's the stuff that we drink, bathe in, etc., is incredibly rare. Only 3% of the world's water is fresh water. 3%. 3%. And 2/3 of that, 2/3 is tucked away in frozen glaciers or otherwise unavailable for our use. That means only one third of 3% of the water on the planet is in fresh water, is in liquid form for us to drink. In a usable, consumable state. Correct. That's right. Now that should be a very sobering prospect. Well, think about the inverse of this. So you've got 97% of the rest of the water on the planet, which is contaminated with sodium chloride. Correct. Now, so if you want to future-proof yourself and your investments, here's my advice to you. And I'm looking at this myself. Invest in a desalination plant. That's what you want to do. Invest in a desalination plant. Get your community together. I don't know where you live. Doesn't really matter where you live, but just get the money together to buy a desalination plant if you can't afford it. I'm investigating it. They ain't cheap. I can tell you that. No. But if you want to future-proof yourself, that's where you invest your money, in water. Now, interestingly enough, the fresh water is sort of disappearing as well. Right? We're going to get into this in some more detail later, but it is disappearing. So the third of the 1%, sorry, of the 3%, is rapidly disappearing. Massive freshwater lakes like Lake Baikal and others are at the Caspian Sea as well. Yeah. They're shrinking. Dave earlier in the first part of the show spoke about the water issues in Nevada, like me, for example. But these water issues are global in nature. The planet is losing its fresh water, and on top of that, which to my mind is an even worst scenario is we're losing glacier-locked fresh water into the ocean.
Yeah.
Now, yes, it decreases the salinity of the oceans, but not significantly.
Not enough.
But we do lose, I guess, readily available fresh water. I mean, if you really needed to, you could mine glaciers, you could mine the polar ice caps. If you really wanted to, you could do that. You could mine. I mean, if push came to shove, that would be a fairly easy undertaking because it's fresh water, so you just mine that. But if it's melting and becoming part of the wider ocean water, right, then you have to go through the process of desalination, which, as I pointed out earlier, is quite expensive and a little onerous. So fresh water is a problem. As a result, about 1.1. These are recent figures. These are, I think, 2020 figures. About 1.1 billion people worldwide, right, lack access to water, now fresh water, and a total of 2.7 billion people. 2.7 billion. That's about a third, more than a third of the world population, find water scarce for at least 1 month of the year. Inadequate sanitation is also a problem for 2.4 billion people. They're exposed to diseases such as cholera and typhoid fever and other waterborne illnesses. 2 million people each year, mostly children, die from diarrheal diseases alone. Many of the water systems that keep ecosystems thriving and feed a growing human population have become stressed. We mentioned this, right? Rivers, lakes, aquifers, they're drying up, or worse, they're becoming too polluted. So that's on us. That's on us. The drying up, that's a mystery, but the pollution, that's all us. More than half of the world's wetlands have disappeared. Now, why is a wetland important? A wetland is a filtration system, right? A wetland is a filtration system for your water, okay? And it's also a storage for fresh water because it does feed into rivers and other things as well, and underground aquifers. Agriculture consumes more water than any other source and wastes much of that through inefficiencies. Climate change is altering patterns of weather and water around the world, causing shortages and droughts, and floods in others. So we've got droughts in some areas and floods in others, but floods aren't good either. Why aren't floods good? Because floods releases enormous amounts of water into the ocean. Because, I mean, water will find its own level. And usually when there's a flood, waters will make their way to the nearest saltwater sea.
It's one of the greatest wastes of water.
Yeah.
Is too much rain, flooding, and washes away your topsoil, your agricultural soil.
Yeah.
And what can you do with it? Nothing. Then it damages everything as well at the same time.
100%. So flooding is not a good thing, everybody, just in case you thought it might be. At the current consumption rate, again, these are 2020 figures, okay? At the current consumption rate, this situation will only get worse. By 2025,
3 years.
3 years, everybody. 3 years. 2/3 of the world's population may face water shortages. 2/3.
Remember Lex,
right,
Mickey? Remember the show Lex?
Yeah, I do actually. Yeah.
Remember how the dude had the vial of it just collected sweat around his neck and he could drink it every once in a while?
Yeah. But that's where we're heading. I mean, the way most of us live, I mean, in Australia we're pretty lucky on the coastal areas, right? Not so much in the middle of Australia, but water is becoming a rare commodity, a scarce commodity in many parts of the world. That's I don't know if you noticed, but Islam requires you to wash before prayer. Right? So you have to wash your face, your hands, your feet, right? If you're an observing Muslim. But because it's a desert religion, you're allowed to do it with sand.
Wow.
Okay. So my point here is that people already are dealing with water shortage. And you know what the Saudis invest in? Right? Water. Why do they do that? Because they're desert people. They don't care about oil. They care about water. If you're half smart, right, you make sure that there's fresh water anywhere, in your vicinity, and you've got access to fresh water, etc., etc. Because, like I said before, Dave, it's an old adage: 3 minutes without air, 3 days without water, and 3 weeks without food.
That's right.
That's what it is. But Dave, tell me about water scarcity.
Water scarcity is often divided into two categories: physical scarcity, when there is a shortage of water because of local ecological conditions, and economic scarcity, when there is inadequate water infrastructure. The two frequently come together to cause water stress. For instance, a stressed area can have both a shortfall of rainfall, as well as a lack of adequate water storage and sanitation facilities. Experts say that even when there are significant natural causes for a region's water stress, human factors are often central to the problem, particularly with regard to access to clean water and safe sanitation. Almost always, the drinking water problem has nothing to do with physical water scarcity, says Georgetown University's Mark Giordano, an expert on water management. He continues, it has to do with the scarcity of financial and political wherewithal to put in the infrastructure to get people clean water. It's separate. At the same time, some areas that suffer physical water scarcity have the infrastructure that has allowed life there to thrive, such as in Oman and the southwestern United States. Mackie, talk to me about... Oh, sorry, go on.
No, but look, if you have the cash, you can make the desert.
Like the Saudis built
the Saudis, the Israelis.
They've built a civilization from oil money.
Yeah, 100%.
And they throw it around like Mr. Burns and Smithers.
That's right. But water to them is sacred, right?
That's right.
It's interesting. I've got a lot of Lebanese friends, and they drink from a bladder, like a water bladder.
Mm-hmm.
But the spout is very small. It's like usually a metal spout, and it's designed in such a way you sort of drink it over your shoulder. It's actually really cool, and it is designed so you don't spill any water. You're not drinking all of it at once either. No, exactly, right. So it's sort of it's a really ingenious way of. And when I first saw it, I go, oh wow, this is really cool. I mean, well, when you're going through the desert, and you need to conserve water, this is what you do. Forget a canteen. This is like it's like a bladder, and there's like a metal spout, maybe silver, I don't know what it is, but and then you just release what you need into your mouth directly without ever touching the spout, though.
Yeah, you squeeze it and the squirt's in there. Yeah.
It's quite something. But yes, thoughts on water. I mean, look, water is essential to our existence. Okay, we are mostly water, obviously, and without water we wouldn't exist. We couldn't, our life, our form of life just wouldn't be possible. And it's also been a spiritual significance in water and in the way we view water, and I guess the recognition that it is such a special substance. Now, the Tao Te Ching, along with the Zhuangzi, is a fundamental text for both philosophical and religious Taoism, and it states the following: the highest excellence is like that of water. The excellence of water appears in its benefiting all things, and its occupying, without striving to the contrary, the low place which all men dislike. Hence, its way is near to that of the Tao, as well as there's nothing in the world more soft and weak than water, and yet for attacking things that are firm and strong, there's nothing that can take precedence of it, for there's nothing so effectual for which it can be changed. Now, what this means is that water will wear away everything, but it will also occupy any niche it can, and so should we. We should be able, humble enough to accept our station. And, that's really the philosophy of teaching. But it's true. Water will wear away everything. It is the most effective solvent that we know. All right, water is incredible in its ability to wear down mountains, Dave. Into river. I mean, look at the Grand Canyon. Look at any river, any kind of little stream that has carved its way through the landscape. And look at the force of water when it does flood. Nothing stands before it. Even if it's moving at a walking pace. Do you remember? I mean, recently we had the Boxing Day tsunami. That was one which affected I guess the South and Western Pacific. And then we had of course Fukushima, which was an explosion, but underwater quake, but then which led to a tsunami. It's like a slow moving tsunami. I mean, this wasn't like rushing water really, but it was just relentless. it just went, and you couldn't stop it. It just goes, right? So it is really an amazing force, and it is such a strange substance. I mean, we look for water everywhere, Dave. From all the planets, we look for water, and we find it here and there sometimes, right? Because for us, it's an indication of life. Now, it's only indication for life as we know it, everybody, because life does not necessarily rely on water to exist. Okay, we know that much. But for our kind of life, impossible without water. But why don't we talk about some of the more, I guess, general things about water, Dave?
Yeah, okay. So let's start with the chemical formula of H2O. It's inorganic. It's transparent, it's tasteless, it's odorless, and nearly colorless. It's a chemical substance, which is the main constituent of Earth's hydrosphere and the fluids of all known living organisms, in which it acts as a solvent. That's one of the most important features of water, is that it's a solvent. It can acquire material. And yeah, very good. It is vital for all known forms of life, of course, on Earth, yes, even though it provides neither food, energy, nor organic micronutrients. Its chemical formula, H2O, indicates that each of its molecules contains 1 oxygen and 2 hydrogen atoms, connected by covalent bonds. That's a pair of bonds. The hydrogen atoms are attached to the oxygen atom at an angle of 104.45 degrees. Water is the name of the liquid state of H2O at standard temperature and pressure. That's once again, Meki covered that off. A number of natural states of water exist. It forms precipitation. It participates in precipitation in the form of rain, and aerosols in the form of fog or clouds. Clouds consist of suspended droplets of water and ice. It's a solid state. So ice is a solid state. When finely divided, the crystalline ice may precipitate in the form of snow. The gaseous state of water is steam or water vapor. It's not truly the gas. It's not H2O gas. You've got to just remember that. It's still water that's in fine particulates. Water covers about 71% of the Earth's surface, mostly in seas and oceans, about maybe 96.5%. Small portions of water occur as groundwater, it's 1.7%. In the glaciers and the ice caps of Antarctica and Greenland, it's 1.7% again. And in the air as vapor, clouds, maybe consisting of ice and liquid water suspended in the air, and precipitation, which is 0.001% of all of the water. But water moves continually through the water cycle of evaporation, transpiration, evapotranspiration, condensation, precipitation, and runoff, usually reaching the sea in a circular pattern of it being evaporated and then turning back into water, etc. But Meki, the properties.
Sure. Now the properties, again, H2O, it's a polar inorganic compound that is at room temperature, a tasteless and odorless liquid, nearly colorless with a hint of blue. This simplest hydrogen, chalcogenide, is by far the most studied chemical compound and is described as the universal solvent for its ability to dissolve many substances. This allows it to be the solvent of life. Indeed, water is found in nature almost always includes various dissolved substances, and special steps are required to obtain chemically pure water. By the way, chemically pure water will kill you. Do not drink chemically pure water. Water is the only common substance to exist as a solid, liquid, and gas in normal terrestrial conditions. So under this gravity, with this temperature and that much pressure. Let me just see. Yeah, I'll take the states.
Go.
The three common states of matter, along with oxidane, water is one of the two official names for the chemical compound H2o. It is also the liquid phase of H2o. The two other common states of matter of water are the solid phase, ice, and the gaseous phase, water vapor or steam. But again, as Dave pointed out, not really. The additional removal of heat can cause phase transitions, freezing, water to ice, melting, ice to water, vaporization, water to vapor, condensation, vapor to water, sublimation, ice to vapor, and deposition, vapor to ice. Have you ever seen sublimation? That's quite something to see. That's pretty cool. Now, there's another state of water, but more of that later. And in fact, that's one I want to throw to you. Okay. Density. Water differs from most liquids in that it becomes less dense as it freezes, as we said. In 1 atmosphere pressure, it reaches its maximum density of 1,000 kilograms per cubic meter at 3.98 degrees centigrade, or 39.16 Fahrenheit. The density of ice is 917 kilograms per cubic meter, an expansion of 9%. This expansion can exert enormous pressure, bursting pipes and cracking rocks. In a lake or ocean, water at 4 degrees sinks to the bottom, and ice forms on the surface, floating on the liquid water. This ice insulates the water below, preventing it from freezing solid. Without this protection, most aquatic organisms would perish during the winter. Now, to be clear, the reason water is the way it is the reason we have life. If liquid water froze from the bottom up,
that means it didn't expand when it froze. The whole Earth would be an ice ball.
We wouldn't exist. There would be no life.
That's right.
There would be no life. Water is a diamagnetic material, though the interaction is weak. With superconducting magnets, it can attain a notable interactions. At a pressure of 1 atmosphere, ice melts or water freezes at 0 degrees Celsius, and water boils or vapor condenses at 100 degrees Celsius. However, even below the boiling point, water can change to vapor at its surface by evaporation, which is vaporization throughout the liquid is known as boiling. So evaporation.
32 degrees Celsius is the point at which water will be able to evaporate very fast. Correct. On its own, with only temperature as a relation rather than wind or dry wind.
Correct. And that's again evaporation. Whereas vaporization is achieved throughout the liquid through boiling. Mm-hmm. Sublimation and deposition also occur on surfaces. For example, frost is deposited on cold surfaces, while snowflakes form by deposition on an aerosol particle or ice nucleus. It's sort of like a pearl. It forms the way a pearl forms. In the process of freeze drying, a food is frozen and then stored at low pressure, so the ice on its surface sublimates. The melting and boiling points depend on pressure. You will find that the higher you move up in the world,
like if you went to the top of a mountain,
the longer it will take for your water to reach boiling point. So
that's crazy.
If you're at the base camp of Mount Everest, your cup of tea is going to take a little bit longer. But Dave, there's something recently that I
know, and I've actually posted one into our chat as well.
Oh, beautiful.
All right, so scientists discover a new phase of water known as Superionic ice. This is inside planets. This is by Alexandra Larkin, 28th of October 2021. Scientists have discovered a new phase of water, adding to liquid, solid, and gas, known as Superionic ice. The strange black ice is, as scientists called it, is normally created at the core of planets like Neptune and Uranus. In a study published by Nature Physics, a team of scientists co-led by Vitaly Prakhpenka, a University of Chicago research professor, detailed the extreme conditions necessary to produce this kind of ice. It had only been glimpsed once before, when scientists sent a massive shockwave through a droplet of water, creating superonic ice that only existed for an instant. In this experiment, the research team took a different approach. They pressed water between two diamonds, the hardest material on Earth, to reproduce the intense pressure that exists at the core of planets. Then they used the advanced photon source, or high brightness X-ray beams, to shoot a laser through the diamonds to heat the water, according to the study. Imagine a cube, a lattice with oxygen atoms at the corners connected by hydrogen. When it transforms into this new superionic phase, the lattice expands, allowing the hydrogen atoms to migrate around while the oxygen atoms remain steady in their positions. The researcher said in a press release, it's kind of like a solid oxygen lattice sitting in an ocean of floating hydrogen atoms. Very pleased with himself, I bet. Using an X-ray to look at the results, the team found the ice became less dense and was described as black in color because it interacted differently with light. It's a new state of matter, so it basically acts as a new material, and it may be different from what we thought, said the researcher. What surprised the scientists most was that superionic ice was created under a much lighter pressure than they'd originally speculated. They had thought that it would not be created until the water was compressed to over 50 gigapascals of pressure, the same amount of pressure inside rocket fuel as it combusts for liftoff, but it only took 20 gigapascals of pressure. Sometimes you are handed surprises like this, said the researcher, the professor. Superionic ice doesn't exist only inside faraway planets, it's also inside Earth. And it plays a role in maintaining our planet's magnetic fields. Huh? What? Earth's intense magnetism protects the planet's surface from dangerous radiation and cosmic rays that come from outer space. Planets like Mars and Mercury don't have magnetic fields, and they are exposed to the harsh weather of outer space. That's why the team thinks learning about superionic ice might play an important role in searching for other planets that can host life. This should stimulate a lot more studies, says the professor.
Now think about that for a second. We always thought, it's just a friction of the potential metal, molten metal inside the Earth's crust mantle that gives us our magnetic fields, etc., etc. It turns out, no, water is also important here, right? And the more we look at this, and the more complex this whole arrangement becomes, to be honest with you, it's like a very finely tuned machine, Dave. Oops, I didn't say that. Said that, crazy people. Crazy people. Tartarians. What? Crazy people. But to be clear, right? This is no, of course they did. Mm-hmm. No, but yeah, you're familiar with the modern day Tartarians, right? Okay, that's a show then. If you're not, that's a show.
It's a
that
show.
Has to come. It's a show. Now the next is an abstract of a study I liberated from the site of SPRING 8, which is the world's leading optical scientific research facility, SPRING 8 or -8. It was published in March 2008, and this is what it says. Water molecules are still shrouded in mystery, unlocking the secrets of the mysterious structure and patterns of motion of water molecules. And this specific abstract was about the reasons for still studying the structure of water. Water is very familiar to us, and its a simple molecular structure, H2o, is well known even to junior high school students. Although it is hard to believe that the state of water has not yet been completely clarified, water is still shrouded in mystery. Although people tend to think that scientific research only targets unknown and novel phenomena, it is an important task of scientific research to attempt to find and clarify mysterious phenomena in common substances such as water and ice. You may be surprised to hear that the structure of water is being studied at SPRING 8, one of the world's leading optical scientific research facilities, as I just mentioned. However, there are good reasons for carrying out such research. Have you ever wondered where ice stores its enormous amount of cold energy for cooling objects? why the density of water is greatest at 4 degrees Celsius and decreases both below and above 4 degrees Celsius. Or why the density of solid ice is lower than that of liquid water. To answer these questions, it is essential to clarify the structure of water, an issue that is still generating controversy. Recently, the structural analysis of water and ice has been carried out at Spring 8, and some new facts that may lead to the resolution of some long-standing arguments about the nature of water have been revealed. That's why we decided to bring you a show about water, because it's the elephant in the room, Dave, like the moon. Like the moon, because this is the thing, though, right? I mean, let me draw you another example before we go on in the text. We all talk about Bitcoin mining. Now, it's my favorite example now, because and nobody ever asks why we do it or what we're achieving by mining the Bitcoin. What is it that we're doing that will? I understand it generates Bitcoin. That's not what I'm talking about. Why? What is it that we're doing to generate the Bitcoin? Is my question. Why are we doing it? And the answer is not to get more Bitcoin. Same with this and the moon. Well, there's the moon, and that's all we need to know about it. And here's water. But fundamentally, we need to ask ourselves why the moon and why water. And especially in the context of where we are, right? I know it's easy to believe that we are insignificant in the face of the cosmos and potentially, the multiverse, etc., etc. But ultimately, there are too many strange things coming together on this planet or the solar system, specifically for our continued existence to be safeguarded, not to be investigated closer. There are too many things. The moon is a complete mystery. It makes no sense. Water makes no sense as a chemical substance. None. Zero. Right? Especially in the context of our dependence upon it. Clearly, I mean, without water, there is no us. Right? And then it's going to get stranger as we're going to talk about water and the memory of water and a whole bunch of other stuff, right? Is this an indication that we are living, in fact, as I always believed, inside an artificial matrix or in a universe specifically created to hold us, right? Again, all of these things, Dave, to me, look too engineered. I know it sounds crazy.
No, it's not as crazy as you might think it is. The premise that the simpler you are, the universe looks simple. Yeah? Water is water, ice is ice. You can put a snowflake on your tongue, turn it into water. If you boil it, it just disappears. Right? You don't see it. You're simple. Yeah? Mm-hmm. Mm-hmm. You start to discover that, hang on a minute, it expands. We kind of think, when does it expand? It expands when it's hot and it expands when it's cold. You're right, Becky. The only reasons preventing the ocean from melting from the bottom up is the fact that it's being prevented from expanding, turning into the ice state. Because the water, at the bottom of the Mariana Trench, for instance, is below zero. But that doesn't matter, because it's not going to go anywhere. It's not going to turn into ice anytime soon. And even salt water can be frozen, just at a different temperature. But there's pools of fresh water on the bottom of the ocean. Have you seen those too?
Yeah.
Where fish are dying. They swim through the barrier, and there's no oxygen and there's no salt, and they die. They run out of breath. Anyway, so the more complicated our thought has been, the actual more complicated the universe has been to us. We can ask more questions, but then as we do, we're seeing a more complicated version of exactly what appeared as the simplest thing that we could possibly imagine. And I think that's fascinating.
Yeah, I completely agree. It gets. I mean, once you.
It's getting. I know. I'm going to start.
Because that's just crazy stuff.
And can you tell me by what I'm reading, if you look at see what I've posted there, to see if we need to add that to the show notes, because that's pretty crazy. All right, water, an enduring
yes, we do.
mystery.
We do.
Yes. I thought you just text me. Yet another theory of liquid water structure raises questions about interdisciplinary, and well, that's a big one, interdisciplinarity, drug design, astrobiology, molecular biology, and geochemistry, and more. No one really understands water. It's embarrassing to admit it, but the stuff that covers 2/3 of our planet is still a mystery. Worse, and this is Philip Ball from Nature, Volume 452, pages 291 to 292. Worse, the more we look, the more problems that accumulate. New techniques probing deeper into the molecular architecture of water, of liquid water, are throwing up more puzzles. This guilty secret has a myriad of ramifications. Water defines the terrestrial environment. It's central to earth and atmospheric sciences, to biology, and to many technologies. The common assumption that water is well characterized has led to explanatory edifices built on shaky ground. The situation of unsatisfactory and intellectually and hazardous in practice. The situation is unsatisfactory. Everyone is agreed that one aspect of water's molecular structure sets it apart from most other liquids: fleeting hydrogen bonds. These feeble bonds that link the molecules constantly break and form above water's melting point, yet still impose a degree of structure on the molecular jumble. That's where the consensus ends. The standard picture of liquid water posits that each molecule of H2o is, on average, bonded to 4 others in a tetrahedral motif. This repeated, constantly reorganizing unit defines a 3-dimensional network extending throughout the liquid. This prevailing view comes largely from neutron scattering studies and computer simulations, and it makes good sense in the light of the unambiguously tetrahedral arrangement of molecules in ice crystals. In 2004, the latest installment in a long line of dissension emerged. Lars Pedersen and his colleagues based at Stockholm University in Sweden published a controversial paper in Science claiming that molecules in liquid water bind on average to just 2 others, forming chains and rings. It was a string theory of water, if you will. Peterson's group used X-ray absorption spectroscopy to probe the local environment of individual oxygen atoms. The interpretation was greeted with skepticism, but the string theory, in inverted commas, won't go away. The Swedish researchers now claim, in work as yet unpublished, that the conventional tetrahedral structure is not the only way to interpret previous data on water structure from X-ray, neutron scattering, and infrared spectroscopy. The string model fits the results too, they say. With physicists and chemists at several institutes in Japan, they have refined their view through X-ray emission spectroscopy. Water, they now suggest, is a muddle of 2 different structures. It is a random soup flecked with tiny icebergs, each comprising 100 or so loosely cohering modules. The clusters, they argue, are relatively open and strongly hydrogen bonded, in keeping with the conventional tetrahedral model. The soup is made from the string structure described in 2004, denser and with fewer hydrogen bonds. Such a 2-state model would fundamentally change our picture of how dissolved substances behave. Non-polar solutes or solutes might be partitioned into the strongly hydrogen bonded clusters, polar solutes, such as ions, would swim in the disorderly soup. The consequences would be felt from geochemistry to industrial processing to colloid science. Biologists in particular would need to take heed, because liquid water, widely acknowledged as the matrix of life on our planet, at least, is not just a passive scaffold. It has many active roles in molecular biology, minutely influenced, gonna kill all these ants, by its structure. Right now, many water researchers dismiss the Stockholm work as a storm in a teacup. They think that the aberrant results will turn out to have some mundane explanation, perhaps simply data misinterpretation. It demands considerable suspension of belief to accept that the conventional picture of water, assembled painstakingly over the best part of a century, is fundamentally wrong, although stranger about turns have happened in science. Regardless of its outcome, this debate is interesting as an illustration, Freudian slip, of how difficult it is to understand water and how widely the uncertainties ripple out. And the dispute is just one of many. For example, does water form two different liquid phases under extremes of temperature and pressure? How does it rearrange its molecules to a surface or to accommodate solutes? Is most of the water in cells structurally akin to the pure liquid at all? Or when these spats dissolve, history leads us to expect others to bubble up in their place. Extraordinary paper there, Mackie.
I know, right? I know. Yeah, it gets better. too anomalous, too strange. The constituency pondering such issues should be far wider than at present. One problem is that even many of those who work on general theories of the liquid state of matter won't go near water. It is too anomalous, too strange. So, it's fine to study the liquid states of all other matter, but water, no. It's like anti-gravity, isn't it? Let's not look at that. It does not do what liquids are supposed to do. It expands on freezing. It's at its densest in the liquid state at 4 degrees Celsius, rather than becoming steadily denser as it cools. It has an abnormally high heat capacity, odd viscosity, and more, never mind the surface tension. Most of these anomalies are rationalized by the standard tetrahedral hydrogen bonded network, but it's still not clear how this delicate molecular interlinking translates to bulk scale behavior. Computer simulations are often used to explore matter's molecular scale character, but for water, these are notoriously sensitive to how the forces between molecules are modeled. There's nothing new in a two-state picture of water. In 1892, well before hydrogen bonding was recognized, Wilhelm Röntgen, and he's the guy that gave us the X-ray machine, by the way, proposed that cold water contains microscopic icebergs in a fluid sea. In the 1920s, Henry Armstrong's hydrone theory propagated the idea of long-lived clusters of water molecules, as did Oleg Samoilov's interstitial model in the 1940s. Most recently, the chemist Wilson Robinson in Texas tirelessly promoted the idea that water is a mixture of two forms until his death in the year 2000. Such ambiguities allow wild ideas to insinuate themselves. The poly-water affair of the late 1960s stemmed from a claim by Russian chemist Boris Deryaguin and his colleagues to have observed a gel-like form of water in small capillary tubes. Even more outrageous were the experiments of high-dilution biological solutions conducted by the late Jacques Benveniste and his collaborators in France in the 1980s. These created the notion of the memory of water, whereby the liquid can allegedly become imprinted with biomolecular information. Still wheeled out in justification of homeopathy, this improbable idea continues to trade on genuine uncertainties about water structure. Do these disputes matter to anyone but those involved? One of the strengths of science is that it can operate in a modular manner. We can make a lot of progress in one direction while deeper questions about fundamental issues remain unresolved. Were that not so, every field would halt until we had a theory of quantum gravity. Chemists can formulate effective models of atomic bonding and molecular structure without knowing nuclear physics. Evolutionary biologists need not grasp the chemistry of genetics. Even many of those who work on general theories of the liquid state of matter won't go near water. But molecular biology depends inextricably on what water is like at the molecular scale. The iconic view of DNA's double helix, for example, is disingenuous. It is only the molecule structure in water. In the gas phase, the helix looks as though a child has stamped on it. Hydration changes, such as removing water from the surface of the molecule, can induce switches in DNA conformation. Recent experiments show that the double helix spontaneously unzips when dragged into a non-aqueous solvent, suggesting that the same might happen in a low water environment. It is likely that nature exploits these properties to manipulate DNA. Maybe, for example, hydrophobic cavities in enzymes assist the unzipping that precedes replication. When proteins bind their substrates, an intervening sliver of water must shift out of the way. This process depends on the structure of the confined water. Moreover, many enzyme binding sites have water molecules attached to the hydrophilic regions. Some of these molecules cede their position to the incoming substrate. Others stay in the binding site and supply hydrogen bonding bridges to the docking entity.
Yeah, I think we've got 3 minutes left.
I don't think we'll make it.
No, I think we'll pause there.
Yeah. Look, hopefully, see, it's always when scientists go, this is hard. I can't really. This is too hard. No, I don't want to do this. You know, it's almost a self-censorship based on the degree of difficulty that people face. Do you know what I mean? Look, I understand. No, I get it. I understand people. You know, it's understandable. People don't want to, work too hard or be too put out by things. But it's quite astounding, in my opinion, that water would present such a challenge to scientists. It is really quite amazing if you think about it for a second. Here we are, 21st century, and we still don't really know about water. We don't know about the bottom of the ocean. We know a bit about it. We don't know about the moon. We don't know about the other planets. There's so many things we just don't know. But one of the most fundamental things, water. You think, oh, we should have figured that one out, right?
I'll stop asking questions.
Not even close, Dave, right?
I know. You're asking too many questions. Like we had it solved. Shush. Just shush. Right? Says a lot of scientists. It'll turn out to be nothing. Don't worry about it. Storm in a teacup. I love that.
Teacup.
Yeah. String theory of water. Hilarious. It'll be the dark matter of water in a minute. That's what I really enjoy, how the position of some scientists have closed the textbook. There's nothing new to know, and they're just a bunch of pork chops. And I could be anything you like. They're just a bunch of silly people researching something that's going to have no result, or doesn't mean it's meaningless to everybody. But truly, when they're talking about two different states of water, where there are kind of planes of crystalline structure within the water molecule itself, where the oxygen atoms create the fixed lattice and hydrogen can swim around in it in like a pool, that I like the idea that is how it is such a good solvent, that it can transport so much within itself. So every droplet of water passing through limestone will take a little bit of the limestone. And in a cave that's dry enough, the tip of the stalactite will grow by that little bit of limestone. And it'll eventually drop. If the cave is too humid and the droplet falls to the ground, it causes a stalagmite, because the lime is then built upon in such a beautiful manner as to eventually cause a pillar to join from the ceiling to floor. It's poetry in my eyes, right? The way that works. But that's indicative of the feature of water, of which we are, 80% or greater as humans? Bags
60,
of salt
yes.
water. 60?
Well, I mean, without we wouldn't be. We'd just be nothing really. I mean, water is just. In fact, is water the difference between life and not life?
Ooh, I like that. It can be. I'll talk about next week about the alternating theories to what other chemicals could be replacing water if we grew up in a different planet. Take care, everyone. Jer Bear is up next with his fantastic show, After Hours. He's in the chat room. Join in. Talk to him while he's on air. We'll see you next week. This has been David Mickey's Shiny Sign Out.